We are here in section 4.3, and number 1 goes like this. We got 8 singles, 12 fives, 10 20s, and $500 bills that are placed in a box. And if a player is to reach into the box and randomly choose a bill, what is a fair price to pay to play this game? So this is an expected value problem. And to get an expected value problem, I'm going to set it up like this. I'm going to take the value and then the probability of getting that value. Make a little table here. So I'll start here. We got 8 singles, so the value of a single is 1. Then we've got 12 fives, so the value is 5. Then we've got some 20s, and then we've got hundreds. All right, those are the values. Now, what are the probabilities of each of these? Well, how many bills do we have all together? We've got, I'll do it up here. Well, we have what? 8 singles, 12 fives, 10 20s, and 500. So here's 20, 30, 35. All right, so there's 35 bills. Now there's 8 singles, so the probability of getting this 1 here is, what, 8 out of those 35. Now there's 12 fives, so there's 12 of these. So the probability of getting a 5 is going to be 12 out of 35. There are 10 of these 20s, so we've got 10 chances out of the 35 to get a $20 bill, and we've got 5 chances, there's 500s out of those. Oh, that is not 100. What number is that? That's 35. So the expected value goes like this. The expected value is the value times the probability, and then we add them all up. So the first one, we got the value of 1. The probability is we'll get that 1 8 out of 35 times, plus, then we've got a value of 5. That will happen 12 out of 35 times, plus, and then 10, that'll happen, no, not a 10. The value was 20. That'll happen 10 out of 35 times, plus the value was 100, and that will happen 5 times out of 35. So when I compute this on my calculator, I get this number here. I get 21.94294287 ... But look, this is money, so we need to round to the nearest hundredth. All right, so this over here is a 2, so I'm just going to round to the 4. So the fair price to play this game is going to be the expected value, and that's going to be $21.94. Number 2 says we got 300 lottery tickets that we're selling for $8 each. Now the person with the single winning ticket is going to get $95. And we want to know what is the expected value for a winning ticket in this lottery. This is an expected value problem, and to set up expected value problems, I'm always going to do them the same way. I'm going to write a little table, value, probability. So let's see, what's happening here? So we've got 300 tickets, and we're selling them for $8 each. So what could happen is the winner here is going to get $95. So could get $95, and the probability of getting that is 1 out of those 300 tickets. Now what else can happen? Well, you pay $8, so you're going to lose $8, and the chances of that are, well, let's see, there's 199 tickets left, right? Because not 199, what, 299. There's 299 tickets left, and we've already taken out one winner, so what's the probability of losing the $8? That's going to be 299 out of 299, right? There's already a winner, so there's a 100% chance the other tickets are going to lose. So the expected value is going to be the value times the probability plus the value, well, -8, times the probability. Now, when I do that on my calculator, I got -7.6833 ... forever. But since it's money, I'm going to round right to there. So I'm going to say the expected value is -7.68. Meaning that if you play this game, every time you buy a ticket, you just expect to lose $7.68. Number 3 tells us that there's a box that has 4 prizes in it. One's worth $5, two are worth $18, and one's worth $130. And a player is going to reach into the box and draw one of the prizes. So what we want to know is, what is the fair price to pay to play this game? Well, a fair price is going to be the expected value. So to find the expected value, as always, we are going to write value and corresponding probability. So we've got one value of $5, one at $18, and one at $130. Now, the probability of getting that $5 prize, well, there's 4 prizes. There's only one of those $5. But the 18 out of those 4, there's 2 of those 18s. But then there's only one of those $130 prizes, 1 out of 4. So the expected value here is going to be the value times the probability. So it's going to be 5 times 1/4 plus the value times the probability, 18 times 2/4, plus the value, 130, times the probability. And I did that on my calculator, and I got 42.75. So what's the fair price to play this game? So just to reach your hand into this box and get a prize, you should pay $42.75. Number 4, we've got a raffle where we're going to sell 1,200 tickets for $4 each, and there's 2 prizes. One of them's $50 and one of them's $400. So what is the expected value for a single ticket for this raffle? So it's expected value, so I'm going to make my little table of value, corresponding probability. Now I see 3 values here, right? I see a value of $50, a value of $400, but also it's going to cost you $4 to play, so that's going to be a -4. Right now, for that $50, there's one ticket out of 1,200 that's going to do that for you. Now, one ticket's gone. Now, what about that $400? Well, there's one chance you're going to get the $400, but there's not 1,200 tickets left, right? You took one out, so there's 1,199 tickets left. Now you've removed 2 tickets. So what's the probability of losing? Well, there's what? There's 1,198 tickets left, right? There was 1,200 to begin with. You took out one, so there's 1,199 left. Now you've removed 2, so there's 1,198 left. And what's the probability of that one right there? Well, that's 1,198, right? The probability, you have how many losing tickets? 1,198 out of 1,198. So here is the expected value. It's going to be the value times the probability plus the value times the probability minus the value, right, 4, or plus 4, plus -4, times the probability. Now 1198, there's 1,198 bad tickets, and there's 1,198 tickets left. So that's just a 1. So that whole thing is just -4 times 1. When I make this computation, I got this. I got the expected value to be negative, all right, 3.624, 3.624, but it's money, so I'm going to round to the nearest cent. So I'm going to say that the expected value here is -3 okay, round off, that's a 4 over there, so 3.62. So what it means is that every time you buy a ticket, it costs you $4 for a ticket, you can expect to lose $3.62 on the average. Well, here's a game that uses a 6-sided die. You toss it, and here's what can happen. If you get an even number, you're going to lose $15. Right, so like if a 2, 4, or 6 comes up, you lose $15. If a 1 comes up, you win $15, and if a 3 or 5 comes up, you win $1. So what's the expected value of this game? So as usual, expected value, how the value and the probability. Now I see 3 values up here, right? I see what you could lose $15, so lose, negative. You could win $15, or you could win $1. Now, what's the probability of losing $15? Well, you're going to lose $15 if an even number comes up. Now, it's a six-sided die, so there's 6 possibilities, and there's 3 even numbers, 2, 4, 6. So there's 3 out of 6 chances that you're going to get an even number. Now, what's the probability of winning that $15? Well, you're only going to get that $15, that 15, if a 1 comes up. So there's 1 try out of 6. And what about that $1? Well, you get that if a 3 or 5 comes up. So there's 2 chances there, a 3 or 5, 2 chances out of those 6. So the expected value is the value, negative 15 times the probability, plus the value, 15 times the probability, plus the value times the probability. And my calculator is showing that that is negative 4.66666 ... But it's money, so we'll round to the nearest cent, the hundredths. So the expected value of this game is negative $4.67. So to play this game, you would have to pay $4.67 to make the game a fair game.